Hello, and this is going to be, I guess it's part 10 of my skywatching series, and it's going to be a response to my last video that I made. In the last one, I attempted to compute the position of the sun, the moon, and the stars if the Earth was flat, and I based it on where the sun was supposed to be on a flat Earth if the sun was directly overhead. And the question I got was, how do I assume the movement of the sun on a flat Earth? And I decided in this video I was going to show how I did it. I've already shown in other videos how I compared it with sun calc and moon calc and how I correlated the computed sun's movement with the sun's movement that I got from my cameras, and they are all in agreement. What I did was modified the code slightly. So this was the original method that I showed to calculate the sun's position, and it's based on the NOAA solar calculations spreadsheet. Again, it's in one of the other videos. It takes all of the required inputs, and from there it will generate the sun's declination and the hour angle. Those are the two main columns from the original spreadsheet that I was using. I am ignoring refraction. It really isn't much of a big deal until you get a couple of minutes before sunset anyway. And when you're dealing with about a 45-degree vertical field of view, as in my case, the refraction wouldn't be noticed anyway. After I calculate where the sun should be in the sky, then I go and I get the declination and right ascension. I have a separate class that converts right ascension declination to altitude and azimuth, and you might see that I've got a few versions. I'm not going to describe this too much. It's an entirely separate discussion. But in short, the way I designed this originally was that whether I want the sun's position, the moon's position, or the star's position, I get the local right ascension and the declination, and then from there they all go through the same conversion method to turn those into altitude and azimuth. One thing that all of these had in common was that they calculated the declination and the hour angle. To answer the question that I was asked, I kind of cheated slightly. So all of this was working for the globe Earth, and I wanted to add the ability to calculate the position for the flat Earth. I moved the class into an implementation, an impl package, and I created an interface which then my original class that I moved implements. Finally, this allowed me to create a separate flat Earth sun calculator. Seeing as the NOAA solar calculator and sun calc both agree to the direction of where the sun is anywhere on the Earth, the flat Earth solar calculator ends up using the globe Earth sun calculator to do all of the heavy lifting for it. At the start, I was trying to figure out a little bit how I could go about implementing something that works for all locations on a flat Earth, and I ended up having all of my flat Earth calculators, this one for the sun, one for the moon, and one for the stars. They implement an abstract class over here. It didn't have to be an abstract class, but I just didn't want this one to be instantiated, and it allows me to choose the latitude, longitude that I feed into the other calculator, along with obtaining various other information. And so you can see the latitude that I use to feed my globe Earth calculator are 0 and 0. So I instantiate my globe Earth sun calculator, and when the flat Earth calculator is asked to generate the direction of the sun for a given time of the year, given time zone, and a given location on Earth, I'm essentially asking the globe Earth calculator to resolve the sun's direction for latitude 0, longitude 0. The rest of these are relatively the same. Use time zone offset is the provided time zone. That way there I don't have to do any local time to UTC time adjustments. Because the sun is calculated for longitude 0, I then adjust for local right ascension, and again in this case is going to be longitude of 0. And then finally, what I do is I calculate the local flat Earth right ascension declination. This is a constant. How far in kilometers do you have to travel if you go along the line of longitude to travel 45 degrees of latitude, and it's 5,004 kilometers. You can see that in part 6, I believe. So the way this works is this is the observer latitude and longitude, and this is the latitude and longitude where the object should appear directly overhead. Again, this is traveling in a straight line on the surface of the Earth. If you were to travel along the same longitude from the North Pole to your latitude, this is going to be the radius of the flat Earth circle. Then I kind of put that on top of a Cartesian coordinate system to compute the observer's x and y positions. As for the vertical offset, it's always going to be 0. I calculate the object in a similar way, but now the object's height is always going to be 45 degrees distance. In my calculations, the North Pole is at coordinates 0, 0, and the 4 Cartesian quadrants would equal 4 different types of hemispheres. From there, I generate an altitude and azimuth as if it was a flat Earth, but because the rest of my code depends on a globe Earth, I take that altitude azimuth and I convert it back into a new right ascension and declination, which is ultimately returned to the code that called it. And the moon and the stars work in the same way. I hope you found this informative, and I will see you again in another video soon enough. So bye for now.